Well, hello, ladies and gentlemen. So we're going to continue on with reacting systems today, and we're going to prepare the groundwork for using or applying energy balance and, if you like, an entropy balance to a reacting system. So we're going to look at what's called absolute properties today. What is absolute properties all about? Well, unfortunately, all the property tables you've used so far in this class, saturation tables, superheated vapor tables, IGB tables, all the numerical values that you have read have not included the effects of the chemistry. They have not included chemical energy. They have not included chemical enthalpy. They have not included chemical entropy associated with the chemical bonds. So you cannot do chemistry problems using the numerical values in the tables thus far. You can apply the energy balance and plug in the enthalpies or specific enthalpies in your energy balance and get the right heat transfer for a combustor or some kind of a problem involving combustion. You won't get the right numerical value because the property tables you've used thus far do not include the chemistry. So we're going to fix that today by showing you how to calculate or include the effects of chemistry in your property values. We're going to do a problem where we calculate the absolute enthalpy, the absolute entropy associated with a gas at a certain temperature and pressure. We'll actually get the enthalpy and entropy, including the effects of the chemistry. Okay? And to do that, we're going to introduce what are called enthalpy and entropy of formation, H naught sub F bar and S naught sub F bar. These are enthalpies and entropies evaluated at standard reference conditions, and they include the effects of the chemistry. They are tabulated in your notes as well as in any good thermodynamics textbook. So these values, these H naught sub F and S naught sub F, these enthalpy and entropy of formation. There's also an internal energy of formation, I'm sure. And those include the effects of the chemistry. So we're going to talk about enthalpy and entropy of formation. We'll do an example, as I said, calculating the absolute enthalpy and entropy, which includes the effects of chemistry. So we'll do an example, calculating the absolute enthalpy and entropy of a gas. And then we'll use what we've learned to apply an energy balance to a reacting system, a system involving combustion, and we'll calculate the heat transfer or the heat released due to the burning of a hydrocarbon fuel. We're going to do propane, for example. Okay? That's the plan for today. So what's this about absolute properties? Well, the problem is that all the U's, H's, and S's thus far that you've seen in your property tables do not include the effects of chemistry. So far, H, U, and S, and that includes S naught. All of these guys so far in your tables, basically almost all the tables in your notes or your textbook don't include effects of chemistry. That's not good. That's not good. That means we can't use the values in these property tables, the IGB air tables, the IGB tables, the steam tables, the saturation tables. We can't use these enthalpies and entropies, specific enthalpies and entropies directly in your energy and entropy balances. You won't get the right heat transfer. You won't get the right work because they don't include the effects of chemistry. So what are we going to do with that? What are we going to do to fix this? Well, so if we take what are we going to do with this? Let's say I have a property diagram here. I have a temperature and a pressure. And I want to know what, for example, H and S are at this state. And this state has a certain temperature and a pressure. Okay, I want to know what these are. I don't know what they are. I want to know what they are. Well, one way to find out what a property is at this state is to know what it is at some reference state. So let's see, I have H and S evaluated at some reference temperature and pressure. So if I know this, H and S at some reference temperature and pressure, and I could find, let's say, so this is delta H as I go from T and P to T ref and P ref. So let's say I can calculate the delta H somehow. That means that H and S evaluated at some temperature and pressure is H and S evaluated at the reference temperature and pressure plus delta H and S as I go from the reference to my temperature and pressure, okay? So any property, generic property, beta at some temperature and pressure is equal to some beta evaluated at a reference temperature and pressure plus a delta beta as I go from the reference state to my state with a temperature and a pressure, okay? Now, the key here is that this delta beta here, this is actually beta evaluated at T and P minus beta evaluated at T ref and P ref. That delta beta and the beta within the delta, that may or may not include the effects of chemistry. The effects of chemistry don't depend on the pressure and temperature of the system. The effects of chemistry are fixed. They are a function of the chemical composition, not the temperature and pressure of the system. So the betas here in this delta beta term, beta is some property, enthalpy, internal energy, entropy. The betas in this delta here need not include the effects of the chemistry. So we can look these betas up in our property tables, just like we've done so far up to this point in the class. So this guy here need not include effects of chemistry. That means we can evaluate this delta beta using tables. The tables that we are used to up to this point. The tables that we're using up to this point, okay? Now, what about this beta at T ref and P ref? This is the one that needs to include the effect of the chemistry. Includes effect of chemistry. Includes effect of chemistry. So that beta there at T ref and P ref must include the effects of chemistry. That one must include the effects of chemistry. The betas within the delta, because we're taking a difference, need not include the effects of chemistry, and we can evaluate delta beta using the property tables that we've been using up to this point. Okay, I'm going to call this beta here at T ref and P ref, which includes the effect of chemistry. I'm going to call this B naught sub F. I'm going to get a special symbol. B naught means it's at some reference state. Sub F means formation. So let me write the equation that I have, and we will put a box around it. For any property, beta can equal enthalpy internal energy, entropy, these are specific, so lowercase. For any property beta, beta evaluated at some temperature and pressure, and this includes chemistry, is equal to B naught sub F plus delta B, and I'm not going to write the delta, I'm going to expand exactly what it is. This is beta evaluated at some temperature and pressure minus beta evaluated at the reference temperature and pressure, where beta, B naught sub F, is the beta of formation. It could be enthalpy of formation, it could be entropy of formation, it could be internal energy of formation. And the reference temperature and pressure, the way these things are measured in the laboratory, reference temperature and pressure are 298 degrees Kelvin, and the reference pressure is 1 atmosphere, which is approximately 1 bar. Okay, so put a box around this. This represents a procedure by which you can calculate or include the chemistry in any of your property values. You find the property of formation, and you find the difference between the property evaluated at the required temperature and pressure and the reference temperature and pressure. Okay, let's do an example here. Let's do an example. I think that's enough talk. Let's do an example. We have H2O vapor in a container at some temperature and pressure, 600 degrees Kelvin and 20 bar. I'm telling you right now that this H2O obeys the ideal gas law, so we're going to be using IGB tables, okay? What are we supposed to find? I'm supposed to find enthalpy, specific enthalpy and specific entropy evaluated at the temperature and pressure, but I want to find the absolute enthalpy and entropy. That means including the chemistry, including the effects of chemistry. This specific enthalpy and entropy will not be the same numerical value that you see in your property tables, your IGB H2O property tables, because we're going to include the effects of chemistry. Okay, so let's get started here. So recall beta at some temperature and pressure, beta is some kind of property, is equal to beta of formation plus beta evaluated at T and P minus beta evaluated at the reference temperature and pressure. And remember here, the betas in this difference need not include the effects of the chemistry. So we can get these from any property tables. Chemistry not included, get from prop table. Get from prop tables, okay? Okay, first of all, I didn't mention it just a moment ago, but no, actually I did. I mentioned the reference temperature and pressure values. So actually we're ready to go. Let's look up some quantities here. Let's do this for enthalpy first. So let's do H absolute first. So this means H evaluated at 600 degrees Kelvin and a pressure of 20 bar. And this is absolute, is equal to the enthalpy of formation plus the enthalpy evaluated at temperature and pressure, or 620 bar, minus enthalpy evaluated at the reference temperature, which is 298 degrees Kelvin, and the reference pressure, which is 1 atmosphere. Okay, so that's the general equation for getting for applied to enthalpy for our particular problem. Okay, beta is equal to H. Beta is equal to specific enthalpy. Okay, let's look up some of these values here. The enthalpy of formation. And this is for H2O. H2O. Let's have a look here. All right, so we've got two places you can find the enthalpies of formation. First place you can find it is at the extreme end of the property table. So if you look at B13, you'll see various substances along with the chemical formulas and molecular weights. You'll see H naught sub F, and it's got an overbar in it. So it's the enthalpy of formation. This includes the chemistry, and it has units of kilojoules per kilomole. That's why it's got the bar on the top, all right? Got the bar on the top. Now, we see for water vapor, the enthalpy of formation is negative 241,820 kilojoules per kilomole. So 241,820. Negative 241,820 kilojoules per kilomole. I need to put a bar on top of that because that is per kilomole. Negative 241,820, okay? Now, let's go here to the property tables, IGB property tables for, here's H2O. By the way, H naught sub F is listed here as well. It's listed in the header of all the property tables, IGB property tables. So you can also find the specific enthalpy here. Let's see here. I need to find H. So what else do I need to find? I wrote H naught sub F up here. I also need to find H. It's going to be H bar. It's going to be H bar evaluated at 600 degrees Kelvin. And I also need H bar evaluated at T ref, which is 298 degrees Kelvin. Notice that for IGB properties, specific enthalpy is not a function of pressure, so I drop the pressure dependence here. Specific entropy is a function of pressure, so I'm going to have to be a little bit more careful when I evaluate the absolute entropy in the second part of the problem. So I've dropped the pressure dependence here because for IGB, ideal gas behavior, enthalpy is a function of temperature alone. Okay, let's see here. So 600 degrees Kelvin. Let's look these up. 600 degrees Kelvin. So 600, screen's a little big. Whoops, here's 600. Here's 600 degrees Kelvin. For H2O, I get 20402, 2042. Let me make sure that's right. Hard to see. 2402 kilojoules per kilomole. 2402. 2402 kilojoules per kilomole. That's at 600. Let's go to 298. Remember, these properties here do not include the effects of chemistry, and they don't need to. They don't need to. The effects of chemistry is in the enthalpy of formation. Okay, so at 298, which is our reference temperature, I get 9904 for H2O, kilojoules per kilomole. 9904. 9904 kilojoules per kilomole. So I want to point out these last two enthalpies, specific enthalpies, came from the property table, B12. And the enthalpy of formation came from the last table. What is it, B13 or something? Or you can get it from B12 as well. I got it from B12. B13, yes, B13. So this one's from B13. Okay, and remember, this is for vapor. They have different enthalpies of formation here for vapors and liquids. So let's have a look at that, make sure everybody's on the same page. So here's B13 for water vapor, enthalpy of formation when the H2O is a vapor versus a liquid. This has to do with the change in enthalpy associated with vaporization, okay? The phase change, the enthalpy change associated with the phase change from a liquid to a vapor, okay? They also have this for some of the fuels. Let's say you're doing a problem involving burning a fuel like octane, or burning a fuel like alcohol, whether it's ethyl or methyl alcohol. So you got to be careful here whether the fuel is a liquid or a vapor. So you got to be careful what your state is. Same thing with ethane and propane. It specifies whether the substance is a vapor or a liquid. Also, I have carbon here. Here's the enthalpy of formation for carbon. That's for solid carbon. Solid carbon. Okay? So you got to be a little cognizant what the state is of the material you're trying to calculate the enthalpy for. Okay, so I'm ready to plug in. Let's see here. The enthalpy of formation is negative. Negative 2. Oh, these are all barred quantities. So if I want to get H, that means I have to divide all of this by the molecular weight. Let's see here. The molecular weight of H2O is what? 18.02 kilograms per kilomole. You can look that up. 18.02 kilograms per kilomole. Yep. Okay, so negative 241, 820 plus delta H. So that would be 2402 minus 9904. And all this has units of kilojoules per kilomole. And then I'm going to divide it by the molecular weight, which is 18.02 kilograms per kilomole. So the kilomoles cancel out, and I'm going to get kilojoules per kilomole. And the final enthalpy at 600 degrees, including the chemistry, is negative 12.84 megajoules. Megajoules per kilogram. So this container here – 112.84 megajoules per kilogram for a temperature equals 600 degrees Kelvin and a pressure of 20 bar. Okay. Let's do the entropy. The entropy, including the effects of chemistry, the specific entropy, including the effects of chemistry. Well, using this equation here applied to entropy, so specific entropy applied at a temperature of 600 degrees Kelvin and a pressure of 20 bar. So this will include the effects of chemistry, is equal to H naught sub F plus S evaluated at 600, pressure evaluated at 20 bar, minus S evaluated at T ref, which is 298 Kelvin and 1 atmosphere, which is approximately 1 bar, okay? Now, my tables clearly are not going to give me specific entropy in kilojoules per kilogram degree in Kelvin. So I'm going to need the molecular weight. I guess I better put it in there right now. So this is 1 over the molecular weight. So let's see if we can find some of this stuff here. Let's see if we can find some of this stuff. Let's look at S naught sub F. So S naught sub F bar. Let's see if we can do that for H2O. Let's find it. Okay, so table B13. Water, vapor, S naught sub F, 188.72 kilojoules per kilomole degree in Kelvin. 188.72. 188.7 kilojoules per kilomole degree in Kelvin. Okay, and that's from B13. B13. Okay, so I got this now. Check. I know what the molecular weight is. I don't need to look that up again. All right, let's calculate this delta S right here. So, what's this delta S, or S from T to T ref and P to P ref? Well, that's equal to, so this is delta S from T and P to T ref and P ref. That's going to be equal to variable specific heats. S naught evaluated at T minus S naught evaluated at T ref. And these are going to be barred quantities minus the universal gas constant ln P over P ref. So that's what this whole term is. Okay, I'm using the S naughts in there. Okay, so I need the S naughts. I guess I better write the whole thing out again. So this is S naught sub F bar plus S naught evaluated at T minus S naught evaluated at T ref. That's 600 Kelvin, and this is 298 Kelvin. And then I have minus the universal gas constant, and then I have P, which is 20 bar, and P ref, which is 1 atmosphere, okay? So I need to look up S naught bar at 600, and S naught bar at 298 degrees Kelvin, which is my reference temperature. Let's go look those up. Okay, table B12. 600 degrees. S naught bar. So 212, 920. That's at 600, and at 298. 298, H2O, 188.72. 188.72. Now, I do want to point one little thing out here. These tables, for those of you that have remembered what I put down for the entropy of formation, these S naught values actually do include the effects of chemistry, but a lot of tables don't. So it's probably the best, regardless of what tables you use, to go through the procedure, looking up the entropy of formation and calculating delta S properly, okay? So for those of you that are paying attention, you'll see that 298 S naught is actually equal to the entropy of formation. So this does include the chemistry. Some tables don't, these do. So go under the assumption they don't and proceed. Okay, so let me write the entropies of formation here. I'm sorry, the S naught for, let's see here. So we had 212.9 kilojoules per kilomole, degree in Kelvin. And we also have 188.7 kilojoules per kilomole, degree in Kelvin. So I got these from B12. Okay? Okay, I think we're ready to plug in. Oh, and I forgot to divide this by the molecular weight. Okay, so entropy of formation, 188.7, forget the unit, plus 212.79 minus 188.7 minus R universal is 8.314 kilojoules per kilomole degree in Kelvin. Natural log 20 bar over 1 atmosphere, which is approximately 1 bar. So I'm just going to put 1 bar there. And this all has units of kilojoules per kilomole degree in Kelvin. And again, it's going to be divided by 18.02 kilograms per kilomole. The kilomoles cancel out, and I get kilojoules per kilogram degree in Kelvin, which is the unit I'm looking for, Let's see here. We get the final specific enthalpy, which includes the effects of chemistry, 10.4 kilojoules per kilogram degree in Kelvin. 10.4 kilojoules per kilogram degree in Kelvin. Okay, 10.4 kilojoules per kilogram degree in Kelvin. All right, so that's how you calculate properties to include the effects of the chemistry. Now I can use these H's and these S's, specific entropy and specific enthalpy. I can use them in energy and entropy balance problems and calculate heat transfers, S dot gen, all sorts of stuff. So the chemistry is now included in the properties, which is what we want, okay? Okay. All right, ladies and gentlemen, let's proceed here. Let's do, now that we know how to calculate enthalpy, specific enthalpy, which includes the effects of the chemistry, let's move on directly to an energy balance problem involving a reacting system. So what we have here is a isobaric combustor. We have reactants flowing in on the right, on the left, and we have products flowing on the right, and we have some sort of a flame here. So obviously, once you burn whatever it is on the reactant side, you're going to release heat. You're going to release heat due to the presence of the flame. So this is hot, so we're going to get a Q dot out being rejected due to the presence of the flame. Now, the temperature of the reactants is 298 degrees Kelvin, and the temperature of the products, so TA is 298, and the temperature of the products is 500 degrees Kelvin. Now, what's being burned here? So we're burning C3H8, which is propane. It's a gas, propane, not liquid propane. It's a vapor. I guess I better put that in. So this is a vapor. And the mole flow rate for the C3H8, the propane, is 0.5 kilomole per second. So N dot C3H8 is 0.5 kilomoles per second flowing in. And I'm mixing it with 11.9 kilomoles per second of air. So N dot for the air is 11.9 kilomoles per second. So this is a reactant side at 298 degrees, 0.5 kilomoles per second and 11.9 kilomoles per second, propane and air. Remember, air contains 21% O2 and 79% nitrogen. So we're mixing it with some air, some oxygen and nitrogen, and we are burning it. And the product is going to be CO2 and H2O. We're going to assume complete combustion here. I've gone through, this is actually a stoichiometric combustion process here. We've had just enough air to completely burn the propane, and I've gone through and I've calculated the various N dots for you for the reactants and the products. Let's see here, if we got 5 kilomoles per second of fuel, propane, being burned with just enough air, stoichiometric air, the mole flow rate for the H2O, the water vapor, is going to be 2 kilomoles per second. The mole flow rate for the CO2 is going to be 1.5 kilomoles per second. The N dot for the nitrogen, so the nitrogen is inert, so 79% of 11.9 kilomoles per second, 79% is 9.4 kilomoles per second. 9.4 kilomoles per second flowing out on the product side. The remaining species or components, the O2 and the fuel, N.O2 and N.C3H8, the propane are 0 here because we have complete combustion. All the oxygen is used up and all the fuel is used up. Okay, that's the way this particular problem is set up. So you don't need to go through and calculate. We're not going to go through and calculate the reaction mechanism. We're not going to go through and calculate the reaction coordinate, epsilon. We're not going to do any of that. I'm just providing you with the N dots, okay? So what are we supposed to find? Let's find the heat release Q dot out. How much heat is rejected or can we extract from this combustion process if the products are at 500 degrees Kelvin and the reactants are at 298. Want to point out here, made the problem even easier, the reactants are at the reference temperature 298. So it just makes some of the calculation of the properties a little bit easier, especially at the reactant side. Kind of simplifies the problem a little bit, okay? But the intake need not be at the reference temperature. This could be any temperature. But that way we don't have to calculate a delta H to get the absolute enthalpy, okay, for the reactants. All right, so let's go to the analysis here. Let's get started. So, analysis. Okay, so let's write the energy balance for our open system combustor. Let me draw the control volume here. Let me draw the control volume. So this is an open system with 2 inlets. Tell you what, that's better. 2 inlets, 1 outlet. Multiple species crossing the outlet, single species flowing in at each port at the inlet. So we have a Q dot minus W dot is equal to E d CV dt. And now I'm going to write the enthalpy flows in terms of mole flow rates. This I have N dots here. So I think I'm going to write everything in terms of moles. So I have the double sum of N dot H bar plus PE bar plus KE bar. These are all on a per mole basis here. And this is summed over all outlets minus the same thing summed over all inlets. Okay? Okay, so I don't see any shafts or wires in this combustor. The combustor shape itself is not distorting. The combustor is not being crushed or expanded. So there's no boundary work going on. So there's no work going on here. I have a single heat interaction, which is a Q dot out. So this Q dot becomes a Q dot out. Actually, it's a negative Q dot out. And there's no work. No work, so that's 0. I'm going to assume steady state, nothing else to assume in this problem. So that goes away. Let's see here. I'm also going to neglect the change in kinetic and potential energy at the inlet and the outlet and for the various components. I have no information on the velocity of the flow or on a change in position, so I'm going to neglect the changes in kinetic and potential energy. Tell you what, I'm going to move this. So assumptions, steady state, delta PE, delta KE approximately 0, and then W dot is equal to 0, okay? So we're supposed to find Q dot out. Okay, well that simplifies things a little bit. So we have negative Q dot out is equal to the double sum over all outlets, sum over all components, N dot H bar. So this is summed over all outlets. Summed over all components, I summed over all outlets. And then I've got minus the same thing, N dot H bar summed over all components, summed over all inlets. Okay, seeing how this is going? This works just like a mixture problem. In fact, this will be exactly like a mixture problem, except we need to be careful calculating the enthalpies. They're going to have to include the chemical energy, chemical enthalpy. Okay, let's look at the outlets here. Let's start with the outlet term. Whoops. We only have one outlet, but we have multiple species flowing across the single outlet. So I have N2, CO2, H2O, and that's it. So I have 3 species or 3 components flowing at the single outlet. So this becomes N dot N2 times H bar N2 evaluated in the products plus N dot CO2 H bar CO2 evaluated in the products or at the outlet, and then I have N dot H2O H bar H2O again evaluated at the outlet in the products. What about the across my inlets? I have 2 inlets. I have 2 inlets here. One for the gaseous propane and one for the air. There's no mixing going on. This is pure propane. This is pure air. So I have 2 inlets, but they're chemically pure. So I'll have N dot C3H8 H bar C3H8, the propane evaluated at the inlet. So this becomes N dot C3H8 H bar C3H8 evaluated on the reactant side plus N dot air H bar air. Now I'm going to be a little bit careful here. The air is composed of nitrogen and oxygen. So at the inlet there, so I'm going to write, where am I going to, I'll do it over there. So let's be real careful here. I'm going to write this in terms of the mole flow rates and the specific enthalpies for the oxygen and the nitrogen separately. So let's be careful. N dot H for the air really is N dot O2 H bar O2 plus N dot N2 H bar N2. That's really what it is. So I'm going to write here plus N dot O2 H bar O2 at the inlet plus N dot N2 H bar N2 at the inlet. Okay, so I'm going to expand out the N dot H bar air term into the individual chemical components. Okay. All right, so let's write down what I got here. Let's write down what I got, and then we'll start chipping away at the various quantities. I'm going to distribute the negative sign, and I'm going to end up with Q dot out equals N dot H bar of the C3H8 plus N dot H bar of the O2 plus N dot N2 H bar, N dot H bar of the nitrogen evaluated at the reactant side. The propane and the air are at the same state, so I can lump them together in terms of they're at the same temperatures and pressures. Okay, so that's why I can include the fuel and the air evaluated at the same state. And then I've got minus a bunch of stuff evaluated on the product side. N dot H bar N2 plus N dot H bar CO2 plus N dot H bar H2O evaluated at the reactant side. Okay? Now let's see what we got here. I have the N dot for the fuel, the N dot for the oxygen at the inlet. N dot O2 at the inlet is equal to N dot for the air at the inlet times 0.21. So it's 21%, 21% oxygen. Let's see here, the mole flow rate for the air. The mole flow rate for the air is 11.9 kilomoles per second. So I get 2.5 kilomoles per second for the O2. 2.5 kilomoles per second. 2.5 kilomoles per second. 2.5 kilomoles per second. Okay, so I have N dot for the air going in. Check. I have N dot for the N2. It's actually the same as N dot. So N dot N2 at the inlet is actually equal to, it's either 79% of N dot air, or you just notice that the nitrogen is not consumed in the reaction. So N dot N2 at the inlet is equal to N dot N2 at the outlet. So that means what? 9.4 kilomoles per second. That's given in our problem statement, okay? So I have that. I have N dot. Yes, I have N dot out. I have N dot for the CO2 and the H2O on the product side. 1.5 for the CO2 and 2 kilomoles per second for the H2O. So I have all the N dots. Check, check. Okay, so I got a lot of stuff here. Let's try to find some of these H's. Let's find the enthalpy H bar of the propane C3H8 evaluated at my inlet condition on the reactant side. So so A, that's equal to H bar C3H8 evaluated at Tref and Pref. Remember, the reference pressure and temperature are 298 Kelvin and 1 atmosphere. So I want to evaluate the enthalpy, specific enthalpy at the reference temperature and pressure. Well, that's just the enthalpy of formation. So this is H naught sub F bar for the C3H8. I can look that up in a table. Let's look it up. Let's find the reference, let's find the enthalpy of formation for our propane. Enthalpy of formation, B13. Propane is here somewhere. Propane, vapor, C3H8, minus 103,850. Minus 103,850. Minus 103,850. And that's going to be kilojoules per kilomole degree in Kelvin. Okay? 103 minus 103,850, and that's from table B13. Okay, now we've got this. Check. What about the enthalpy of formation for the nitrogen and the oxygen at A? Let's see here. H of the N2 at A. Well, again, the reactants are all at the reference temperature and pressure. I'm telling you, it's at 298. That's the reference temperature. So this is H evaluated at T equals Tref, which is 298 degrees Kelvin. So that means the enthalpy, specific enthalpy, is equal to the enthalpy of formation at the inlet. So H naught sub F bar for the nitrogen, N2. So we are at the reference condition at the reactant side. So I'm going to go to nitrogen here. If I can find it. Nitrogen, N2 vapor. Enthalpy of formation, 0. Well, that's easy. So this is 0. So this term goes away. What about the enthalpy of formation for the O2? Specific enthalpy of the O2 at the reactant side. So HO2 bar at the reactant side. That's equal to H bar evaluated at T equals Tref, 298 Kelvin. So let's look up the, well, which is the enthalpy of formation for the O2. We are at the reference temperature, so H bar is equal to the enthalpy of formation for the O2. Let's find it in the table. Oxygen, vapor, it's also 0. Okay. So now this term's 0. That term's gone. Okay. All right, let's find some of these other enthalpies, H bars. Let's find some other ones. I need a little bit more room here. Tell you what, I'm going to move over to the other board. You just remember what we're looking for, which is Q dot out. We're looking for Q dot out. So let's find the enthalpy H of N2 at the product side. Let's find H of the N2 in the products. Let's find that. So H bar of the N2 on the product side is equal to H bar of the N2 evaluated at a temperature of 500 degrees Kelvin. Okay? And that's going to be equal to the enthalpy of formation for the N2 plus H bar of the N2 at 500 degrees Kelvin minus H bar of the N2 evaluated at 298 degrees Kelvin, which is our reference temperature. Remember, the outlet's at 500, the products are at 500 degrees Kelvin. They are not at the reference temperature, 298. Okay? Let's see here. The enthalpy of formation is, we already looked it up for the nitrogen, it's 0. And then I look up H bar at 500 and 298. Let's see if we can find them here. So we go to B12. 298, nitrogen. What is that? That's oxygen. Here's nitrogen. So at the reference temperature, 298 is 8669 kilojoules per kilomole, and at 500, it is 14,581. 14,581. So this is 14,581 minus 8669. 8669. And that's going to be kilojoules per kilomole. And I get 14,581 minus 8669. And I get 5912 kilojoules per kilomole. So that's H bar of the N2 at the outlet. Oops. There you go. 5912. So that's H bar at the outlet. So now I've got this. What about the rest of them? What about H bar of the CO2 and the H2O? H bar CO2, and that's in the product side. That's going to be the enthalpy of formation for the CO2 plus H bar evaluated at 500 degrees Kelvin minus H bar evaluated at 298 Kelvin. Let's look up some of these quantities here. Let's see here. Carbon dioxide, CO2, 500 Kelvin. Oh, I'm sorry. Enthalpy of formation is negative 393,520. So this is negative 393,520 plus H bar at 500. So that'll be 17,678. Minus H bar evaluated at the reference temperature, which is 298. That's 9364. And that's all going to have units of kilojoules per kilomole. Okay. So 17678 minus 9364 minus 393,520. And I end up with negative 385,206. Negative 385,206 kilojoules per kilomole. So that's H bar for the CO2. Check. H bar for the H2O. Oops. Sorry about that. Negative 385,206. H bar for the H2O at the product side, that's going to be equal to the enthalpy of formation for the H2O plus the specific enthalpy at 500 Kelvin minus the specific enthalpy at 298 Kelvin. I got to get that. Let's crank that out. Let's look at the H2O. H2O. Oops. Sorry about that. There we go. So H2O, that's that one. That one right there. Enthalpy of formation, negative 241,820. Negative 241,820 plus specific enthalpy at 500 minus that at the reference. 500 for, oops, losing it here. 500 for the H2O is 16,828. 16,828 minus at the reference 9904. We looked that up before. And that all has units of kilojoules per kilogram. Running out of space here. Let me crank this out. Crank this out. So 16828 minus 9904 minus 241,820. And I get negative 2, 3, 4, 8, running out of space, 96 kilojoules per kilomole. Running out of space. Negative 234,896 kilojoules per kilomole. Sorry about that. Getting kind of small. Okay, now I have everything. Oh boy. Okay. Let's plug in. Let's plug in. N dot for the C3H8 at the inlet. That 0.5 kilomoles per second. The H bar of the propane is negative 1038.50. And that's going to be kilojoules per kilomole. Notice we're going to get kilojoule per second, so we're going to get watts in all the terms here, which is what we want. Okay, plus. Oh, don't have to worry about these. Okay, so that's the reactant side. put a bracket around that. And then I have minus a bunch of stuff from the product side. Let's see here, n dot N2, that's 9.4 kilomoles per second. And then H bar for the N2 at 500 degrees, 5912, 5912. I'm going to stop writing the units here. N dot for the CO2. Well, that's given. N dot for the CO2 is 1.5 kilomoles per second. N dot CO2 in the reactant side, 1.5 kilomoles per second. Kilomoles per second. And H bar for the CO2 on the reactant side at 500 degrees. H bar for the CO2 is negative 385,206. Negative 385,206. And then I got the H2O, N dot for the H2O is 2 kilomoles per second. And we just calculated H bar for the H2O. That's minus 2348.96 kilojoules per kilomole. And you crank that all out and you get a heat transfer rate. You get a heat transfer rate of 940 kilowatts. 940 kilowatts, or if you like, 0.94 megawatts. So Q dot out is equal to 0.94 megawatts, about a megawatt. Okay, there you go. Very simple, not really much going on there that's different than mixtures, except we have to be careful in evaluating the absolute enthalpy of the reactants and the products. If we don't include the chemistry in the enthalpy calculation, we're not going to get the right heat transfer. I mean, notice all these are huge numbers. The huge number, the CO2 and the H2O, I'm sorry, the H2O and the CO2, those enthalpies, and the fuel, the enthalpies there are large numbers. Forget the sign, they're large numbers. And they're large because they have the chemistry included. They have the enthalpy of formation included in the calculation. So Q dot would be completely different and incorrect if you didn't include the enthalpy of formation. All right, ladies and gentlemen, I think that's enough. Next time we'll do a slightly more complicated problem. Okay, I want to move along and do one more thing for you. However, I do want to point out I just made a mistake on the units for the previous problem. The answer should be in gigajoules per second, not megajoules. I somehow lost 10 to the factor of 3 there. So the heat output is actually 0.94 gigawatts, not megawatts, gigawatts. Okay, so I lost a 10 to the 3 there, a little bit sloppy on my units. So make sure you write gigawatts on there instead of megawatts, off by 10 to the 3. Okay, so that's the heat output, gigawatts. I want to change this problem just a little bit. We're going to keep it all the same, except I'm going to change the product temperatures from 500 degrees Kelvin to the reference temperature. So I'm going to modify this problem. So the products are now going to be at the reference temperature, which is 298 Kelvin. Okay. And therefore, the enthalpies we have here are a little different. Let's see here for the N2 at the outlet. The H at the outlet, the temperature, outlet temperature is not 500 anymore, it's 298. So the delta H goes to 0. In the enthalpy term for nitrogen, so we have, so this is now gone. So we have specific enthalpy, H bar for the nitrogen at the outlet is 0 plus 0. So 0 kilojoules per kilomole. On the CO2, the delta H term is now H at 298, the reference temperature, minus H at 298, the reference temperature. So this is 298. So the delta H term is now 0, and I can get rid of this, and all I have is the enthalpy of formation. Same thing for the delta H term on the water vapor at the outlet. Okay? Now, when I plug these new enthalpies into my energy balance, I find that the heat transfer rate, Q dot out, is now 1,022 megajoules per second, or if you like, 1.02 gigawatts. That's my heat transfer out. So what's the situation here? We have a combustor. I have an N dot for my propane, C3H8. The inlet state is at Tref. The outlet state is at Tref. I have various products of combustion, CO2, H2O. So I have CO2 and H2O. Remember, the H2O is a vapor. It's stoichiometric combustion. So this is stoichiometric combustion. Stoichiometric combustion. Products temperature and reactant temperatures are all at the reference temperature. That's the situation. Let's calculate the heat transfer out. And also I have my Q dot out is 1.02 gigawatts. That's what I've got in the situation here. Let's divide the heat transfer. The heat transfer required to cool the products back down to the reference temperature. If my intake, my reactants are also at the reference temperature, let's calculate the quantity Q dot out divided by N dot, no, not N dot, M dot fuel, which is equal to Q dot out divided by N dot for the fuel times the molecular weight for the fuel. In our case, this is propane. So this is going to be Q dot out, N dot C3H8, molecular weight of the C3H8. Let's see here, I get 1.02 gigawatts. My N dot for the fuel, what? Well, that was 0.5. So half a kilomole per second. Half a kilomole per second. So 0.5 kilomole per second. And the molecular weight molecular weight of propane. Let's find the molecular weight for propane. Let's see here. Molecular weight for propane. Oops. Propane, vapor. Molecular weight, 44.09 kilograms per kilomole. 44.09 kilograms per kilomole. 44.09 kilograms per kilomole. So the unit here is going to be, the kilomoles will cancel out. The gigawatt is a gigajoule per second. So the seconds cancel out. And I get gigajoule per kilogram. This is going to have a unit of a gigajoule per kilogram. Gigajoule per kilogram. So 1.02 divide by 0.5 divide by 44.09. And I get 0.0463. And that's going to have units of gigajoule per kilogram of fuel. I can write this in terms of megajoules. How about 46. Do I have the right unit here? Yeah, 46.3 megajoules per kilogram of fuel. 46.3. This quantity here, Q dot out divided by the flow rate for the fuel, is called the heating value. It's called the heating value of the fuel. It's the amount of heat released, total heat released, or total potential for heat release due to the burning of the fuel. Heating value equals heat released divided by m dot for the fuel. And I want to point out here, both the reactants and the products are at the reference temperature. T products equals T reactants, all equal to the reference temperature. Okay, that's the definition of the heating value. So we have a heating value of 46.3 megajoules per kilogram of fuel. Let's have a look here for a second. Whoops. Let's look at another quantity in our table B13. Look at this, last two columns. Heating value, HV, heating value, units, kilojoule per kilogram. What's the H and what's the L for? H refers to higher heating value. L refers to lower heating value. What's the difference? The difference is the state of the H2O in the products. If the H2O is a liquid form, then we get the maximum heat out of the reaction. If the products, the H2O in the product is a vapor, we get less heat out of the reaction. So the lower heating value here refers to the H2O in the products being a vapor, and the higher heating value refers to the H2O in the products being a liquid. Now, we have propane. Lower heating value, our exhaust H2O is a vapor, so we want the lower heating value. From the table, I see 46, change that into a mega, I see 46.3 megajoules per kilogram. 46.3 megajoules, not kilo, megajoules per kilogram. So the table B13 says that the lower heating value, and this is from table B13, is 46.3 megajoules per kilogram of fuel. That's the established figure. The established figure for the lower heating value for propane. Note, very similar. So this is very similar, exactly the same, more or less, as what we calculated using the energy balance. So we recalculated a quantity which is tabulated in table B13, okay, the heating value. So again, let me make sure you understand the difference between lower versus upper heating value. So the higher heating value, that is the higher heating value. And what that implies is H2O in products is liquid. So the H2O formed by burning the propane or any hydrocarbon fuel ends up as a liquid in the product. So we can extract out as much heat as we can from the products. The lower heating value, so this is lower heating value. We're extracting out less energy so that the products, the H2O in products, a vapor. Okay, so we can extract out less heat from the flow because the products are H2O in the products is a vapor, okay? So I would put a little box around this. This is the definition of heating value. Lower heating value, the products of in the H2O. The H2O in the products is a vapor. Higher heating value, the products is a liquid. H2O in the products is a liquid. And the definition of heating value is the heat released per unit mass flow, where the products and the reactants are both at the reference temperature 298. Okay? All right, that's all I got to say for today. So we've covered enthalpies of formation, absolute enthalpy, the energy balance, heating values. We had quite a day today. A lot of stuff going on. We'll talk about something called the adiabatic flame temperature. We'll talk about that next time. What we're going to do is we're going to set Q dot equal to 0 in the combustor. No heat transfer. We're going to insulate the combustor. And we want to know what the outlet or product temperature is. How hot is the exhaust? The temperature of the exhaust is called the adiabatic flame temperature. It will be in the thousands of degrees. When you burn a hydrocarbon fuel, the heat released increases the exhaust temperature to thousands of degrees, and that's referred to as the adiabatic flame temperature. The exhaust temperature, when there's no heat transfer, is referred to the adiabatic flame temperature. We'll do that next time in the last lecture.